allocation of indexes networks, file sharing in peer-to-peer networks, medium access in wireless networks, and now on Sparse networks. So,
okay. Hello. Yeah. Thank you for the kind introduction. Thank you for inviting me back to Cambridge. I was here last in 2004 doing an internship in Microsoft Research, and it feels good to be back. Today I'll talk about something that's at the intersection of kind of two of the fields I like to work in, which is networks and machine learning. And the idea here would be to use some techniques from machine learning, or specifically high dimensional statistics, to solve a problem that is more motivated by networks. And the problem is clustering sparse graphs. It's joint work with my student and postdoc. I'm sorry, I'll just make this Mr. Shun Yudong, who is now a postdoc at Berkeley, and a postdoc Wan Shu, who is now a professor in Singapore. Okay, so please feel free to stop me at any time. I don't have too many slides, so I'll be happy to answer questions as we go. Okay, so what is graph clustering? So it is what it sounds like. Given a graph, we want to partition the nodes so that there is a higher density within partitions and lower density across partitions. And so I have tried to represent this represent the graph by its adjacency matrix. So this is what a given graph might look like. And if you reorder the rows and columns, which is the same as partitioning the nodes, it will actually look like this. So these two are the same except for reordering, right? And so we just want to partition the nodes so that you can find the kind of denser subclusters. So this is a classic problem. It comes up in a huge number of applications. So some obvious ones are community detection in social networks. It also comes up in recommendations, as was mentioned yesterday, that you may have user groups and you may have item groups, and each group within a user, the people within a user group might have similar preferences for different item groups, but then these might differ across different users. Right? And so you may want to do recommendations as well. You use this as a pre-processing to do more sophisticated recommendation algorithms. So this is a classic problem. We are interested in the sparse case. So what sparse means is everything is sparser. So the density within a cluster is less, and the density across clusters is also less, right? And the difference between them is also less. So sparsity makes the problem harder because the signal to noise ratio, in a sense I'll make precise, is lower. Okay, so I'll present a new algorithm for this, and we will evaluate that algorithm in a classic setting, which is the planted partition model or the stochastic block model, right? And it's a natural extension of Ordau-Shreni to a clustered setting. Right. So this is the planted partition or stochastic block model. You have nodes which are already a partition. So I'll call this the underlying partition. Right. And then a random graph is generated on this, where between any two nodes which are in the same partition, you have a probability p of there being an edge, and for nodes which are in different partitions, you have a probability q. Right. Now, this is the simplest version of this model. There you can make it more complicated, and we'll see how to make it more complicated, but for most of the talk I'll talk about the simple model. This is the simplest model. Okay, so nodes are divided into partitions, and then between any two nodes in the same partition there is a probability p of there being an edge, and between any two nodes in different partitions there is a probability q, and p is bigger than q, and the random graph is given to you, and you have to find the underlying partitions, right? So that's the clustering task. Okay, and we'll be interested in the case where you want to find the partition up to every last node, right? But an alternative objective could be where you partition most of the nodes, but those two differ by a log n factor in terms of the various quantities of interest. Okay, so what are the quantities governing the difficulty of this problem? So p, q, and k are the other quantities. P is the probability of inside, Q is the probability of across, and K is the size of the cluster. Right? So it's clear that if P and Q are very close, it's going to be hard to identify the clusters. It's also pretty clear that if the cluster you want to detect is really small, it's going to be really difficult to do so, right? Because it's going to be hidden by the noise.
Can you just say one more time what P is the probability of?
Okay, so we are generating a random graph, right? And so the way we generate it is we have nodes in say 3 partitions here, and now between any 2 nodes in the same partition, there's a probability P of there being an edge, and across partitions it's Q. So P is the probability of an edge within a partition, of 2 nodes within a partition, and Q is across partitions. Okay? Yeah, and K is the minimum size of a cluster that we want to detect. Okay, so let's try to build up some intuition for this problem by considering what is pretty much the dumbest algorithm, which is well, it has a name. It's called S-link, but it's maybe the first thing you would come up with, which is you say 2 nodes are in the same cluster or the same partition if and only if the intersection of their neighborhoods is large enough. Okay, so I mean, as you can see, if there are 2 nodes in the same partition, they'll have on average a larger size neighborhood than 2 nodes in different partitions.
What is neighborhood relation?
So we have a random graph, right? So the neighborhood of a node is all the people it's connected to.
Flow of its neighbor.
Yeah, one hop neighbor. Yes, exactly. One hop neighbors. Yeah, the people that node I has an edge to. Okay, so for 2 nodes that are in the same partition. So now if I and j were in the same underlying partition, then the expected value of the intersection set, you can calculate it. So the number of people which are the number of other nodes in the same partition as I and j is k, or whatever, k minus 2. So and the probability of there being an edge from I to each one of those is p, and of j to each one of those is p as well. So the number there is k times p square, and for the remaining nodes it's n minus k times q square. So this is the average size of the intersection of neighborhoods if I and j are in the same partition. If I and j this is the sum of Bernoulli random variables, and so the variance is basically also the same. Right? I've said approximate because we are in the small p and small q regime. For 2 nodes in different partitions, on the other hand, you can also calculate the size of the average intersection set, and it will be different quantity. It will be 2k times pq minus n minus 2k times q square. So these are pretty easy calculations to do. Okay, so when does this algorithm work? So for this algorithm to work, you need the difference between the 2 averages, which is k times p minus q square, to be bigger than the standard deviation of each of those quantities, right? And the standard deviation is on the order of n times p square. This is no algorithm. Oh yeah, so the algorithm is, yeah, so this is the trivial algorithm, which is that 2 nodes are in the same partition if the intersections of their neighborhoods is big enough. So
what is algorithm? You said algorithm.
This is the algorithm.
To detect?
Oh, to detect if I and j are in the same cluster or not, right? So if the intersection set is big enough, we say that they are in the same cluster, and otherwise not. And the question I'm trying to answer here is, when can we expect there to be some threshold for which this algorithm has a good probability of success?
This isn't an equivalence relation, is it?
Sorry?
This isn't an equivalence relation.
No, it's an approximate relation. Like this is approximately equal to that.
But how do you actually decide on the cluster? It's not an equivalence relation. It's not transitive. Right? So
Right. This is not transitive. This is just this is answering an easier problem of are I and j in the same partition or not.
fixed I and j.
Fixed I and j.
I see.
Fixed I and j. Yeah. This is fixed 2 nodes I and j, and then fix a threshold. Right. Right.
Are P, Q, and K going to scale with n?
P, Q, and K are going to scale with n.
So a reasonable way would be K fixed, P fixed, and Q like 1 over n. Is that?
If P is fixed and Q is very small, then it's very easy. Yeah. So we will come to scaling questions in a bit, but all 3 quantities have to, it's a relative scaling that matters, and we'll see what that is. It's right here. Yeah, so this is a dumb method which we just pick two nodes, fix them, and say, okay, are they in the same partition or not? And the way I'm going to decide it is by seeing the size of their of the intersection of their neighborhoods. And if that's big enough, then I'll say yes, otherwise I'll say no. Now, what's the likelihood that it will succeed for these two nodes? And for it to succeed with good likelihood, the difference between the expected difference between the two hypotheses should be bigger than the standard deviation. Right? So the expected deviation is k times p minus q square, and the variance is n times p square. And so for this algorithm to work, we need one to be hopefully a little bit orderwise bigger than the other. Right? So I'm like hiding log factors here. That's why I have this funny sign. But this is what pretty much we need for this dumb algorithm. And we can rewrite this to say that it's p minus q square divided by p should be bigger than square root n divided by k. Right. So this is this shows how the quantities p, q, and k affect the success or failure of this algorithm. And now you could let them scale with n as you please. You just need this to hold.
I'm a little confused though, because if p is approximately equal to q,
Yes.
we cannot really talk about communities, or can you?
Yes, sure you can. I mean, all you need is this relation.
Within your community, you're more densely connected than
Yes.
outside of your community.
Yes,
And
yes.
if p and q are the same,
Oh, they're not. Okay, if they're exactly the same, then yes, you cannot. But if one is double the other, it makes sense to talk about it.
Well, yeah, on that topic or related question is, indeed, if P equals Q, what is just the natural, I guess this would be like asking, what's the conductance of just a standard Erdos-Renyi graph? And that even if there were no communities, to what extent does there still exist a partition where it looks as if there were communities?
That does not.
So
Yeah, so I mean, what that means is, there'll be no hope of finding a transitive solution. Like if I do this for every pair I and j, and if this condition holds, then you will be able to find a solution that is actually a clustering, in the sense that
I'm saying just taking
Yeah.
a step back and saying, suppose I just take an Erdos-Renyi graph standard where there's always the same edge probability.
yeah, then for some pairs it will say yes, and for some pairs it will say no, but then the answer will be garbage.
So I guess I'm saying just even taking just a step back to understand the context of the problem, if I looked at all possible ways to split my n nodes into two communities, how good could I do in that it's almost like accidental communities or the illusion of communities somehow?
Yeah, well, if you do only two communities, it will be, I mean, the empirical densities within the communities will be pretty close to the true densities, which means that there will be almost no difference between them.
Even if you looked at the best partition possible?
Yeah.
Okay.
It's just a union bound, yeah.
Okay.
Okay, so so this is the relationship that matters for this dumb algorithm. Okay, so hopefully we want to do better. Okay, so here is another popular way to do better, and it's based on a classic observation, which is that okay. So here's the problem, right? We are given a random graph, right? I mean, we're not given this ordering; we're given this permuted. But let's think of it. We're given a random graph, and we want to we want to find an underlying partition, which I'll represent by what I call a cluster matrix. Right. So this is so every underlying partition can be represented as a cluster matrix, which is a matrix of block diagonal ones, right, and zeros everywhere else. So given this, we want to find this, but what this is you can think of it as this plus error, right? And so what we really have here, one way to view it is if you look at the adjacency matrix, then it's a perturbation of a low rank matrix. So this is a classic observation, and it's the basis of what are called spectral algorithms for clustering. So here is a generic spectral algorithm. I mean, there are a huge number of spectral algorithms, but they're all variations on this theme, which is take the adjacency matrix or the Laplacian and take its singular value decomposition, and retain the top R eigenvectors, and then represent every node as a point in R dimensional space, with the point being the corresponding value of the eigenvectors, and do something simple and local in that space. So let me illustrate. let's say first we were given the stupidest problem, which is it's already block diagonal. Right? In this case, the top R, in this case R is 4, the top 4 eigenvectors will be exactly this. So now if I represent every node as a point in 4-dimensional space, then the nodes of the first cluster will be 1 0 0 0, 1 0 0 0 0. In the second cluster will be 0 1 0 0. In the third cluster will be 0 0 1 0, and so on. Right? So this clearly works. Right? Okay. Now, if you look at and now we start moving away from this. So this is maybe what is called dense graph clustering, where you have some probability p within a cluster and q outside. So it looks like a noisy version of this, and that's represented in the eigenspace as well. Right? So now again, if I represent each point by its corresponding coordinates in eigenspace, then the points in the first cluster will not be exactly 1 0 0 0, but they'll be close to that point, and so on. Right? And so now if I look in this 4-dimensional space and say I do simple nearest neighbor clustering, hopefully that will give me a good clustering of the overall graph. Right? But as you can see in this simple pictorial example, and as you can believe, as things become sparser, this becomes much noisier. Right? So these are spectral algorithms, and this kind of just illustrates how they work.
How does it take R? Just plan the nether?
Let's say R is given to you. Right? I mean, it's pretty easy. I mean, these are pretty fast, so you can always search over R or binary search over R.
How do you choose? How do you make a first preliminary selection of this?
Oh yeah. So what you do is you take an SVD of the matrix, right? And so the matrix that's given to you is a permutation of this. But if you take the SVD, it will just be a permutation of this matrix. If you take the top 4 eigenvectors, it will just be a permutation of this. So that's fine. Okay. Okay. So what is the spectral SNR, or what is the quantity that determines whether you succeed, whether this kind of a algorithm succeeds or fails? Right, so let's try to find that out. Okay, so if I have an adjacency matrix which is zeros and ones, the leading eigenvector is just the all ones, right, which is a useless quantity. So let's just center the matrix by subtracting out the average. Right? Okay, so now we have a new matrix A hat ij, which is Aij minus the average of the entire matrix, and the average of the entire matrix will be pretty close to the quantity there, which is q times k p minus q divided by n. Okay, it's pretty easy to calculate. Okay, so what is the signal now? The signal is the eigenvector that corresponds to one of these partitions. Right? So it's given by this quantity, where 1c is an all ones vector which which has support only on one of the clusters. Right? So ideally, so if there was no noise, then that would actually be an eigenvector. Now that there is noise, it is not an eigenvector, but still you would like there to be a good eigenvalue in that, or a good spectral component in that direction. Right? So this is a spectral component along one of the true clusters, and you want it to be pretty good. So what is its value? Its value is approximately k times p minus q. Okay. What is the noise? The noise, on the other hand, is the largest eigenvalue of the perturbations, right? And the largest eigenvalue, and the perturbations are an IID random matrix where every element has variance on the order of p. So by IID random, I mean every element is independent and the variance is about p. Right? So the largest eigenvalue of such a matrix is on the order of square root n times square root b. Okay. So your algorithm will fail when one of these noise directions, which has nothing to do with the underlying clustering, will be bigger than the spectral direction in that has something to do with the clustering. Okay, so k times p minus q has to be bigger than square root n times square root p, which if you reorganize looks like this. Okay. And you can compare this to what we had before for the dumb algorithm. So this, the right hand side is exactly the same, but the left hand side here we have taken a square root, and the left hand side is smaller than 1, so this is better by a polynomial factor, right, over the dumb algorithm. So this is what we can expect spectral algorithm, which means algorithms which replace the cluster constraint by a low rank constraint. This is what we could hope that they would be able to do. However, no spectral algorithm to date has actually been proven to get this performance. I'm not talking about log factors, even polynomially. It's been very hard to prove that the procedure I just described actually works. And the reason is because of the second step, right, where you need to do something local in eigenspace. That makes the problem really messy. Right? And kind of the main result of our work, which is our algorithm and our analysis, is that we are able to achieve this. We also have a spectral algorithm in the sense that we use low rank structures, and we are able to show this scaling. Okay. So this scaling also happens to be the state of the art for any problem in this for any algorithm in this space, spectral or otherwise, right? And so there's a long history of work on this method, and we have kind of summarized it in this table in terms of two quantities of interest. One is the minimum cluster size, and the other one is the difference in densities. Okay. So the minimum cluster size. So like both quantities are in order of scaling sense. What n by 2 means is that this is a paper only about dividing into two clusters, while n means that you can have a constant number of clusters, but it doesn't have to be just two. Right. So what we want is that the first column should be as small as possible, and I guess the second column should also be as small as possible. The smaller each algorithm is in both these columns, the better it is. Because it can detect a sparser graph with a lower density difference and with a smaller number of communities. Right. And so the state of the art in the first column was square root n, and we also are able to achieve square root n. In the second column, the state of the art was that the p minus q should be square root p times n squared divided by k cube, and we improved that to square root p times n divided by k, and k is the minimum cluster size, so it's on the order of square root n or bigger. So this is better than that. Okay, so what is the method? The method is pretty much what you would come up with if you were looking at this as a statistician, right, as opposed to a computer scientist. So essentially what we have is we have an underlying parameter, which is the cluster matrix or the underlying partition, and we have random observations, and from it we want to find the parameters. So you should do maximum likelihood, and so that's so the starting point of our method is maximum likelihood, right? So we can write, so this is what maximum likelihood is. A is the observed adjacency matrix, y is the underlying cluster matrix, and we want to maximize over y of log of the probability of what we saw. Okay, so if you simplify it, then this probability is the product of two quantities. One is all edges between nodes where both endpoints are in the same cluster. Right? So if both endpoints are in the same cluster, that means that yij is 1, and then the probability that we see an edge is p, and the probability that we don't see an edge is 1 minus p. And so it's p times aij and 1 minus p times 1 minus aij. Right? And there's a similar term for across cluster edges where the two endpoints are in different clusters, and then it's q. Okay, so this is likelihood, And so how do we start converting this to an actual algorithm which operates on a given adjacency matrix? Right? So the first step is just rewriting the terms in terms of y instead of a. So you can just group these terms differently. So now this is the product over all edges where the observed adjacency matrix is 1, and is p times yij, q times 1 minus yij, and similarly that. So it's just a reordering of those terms, right? And we can just so this is just a rewriting of maximum likelihood.
Power was a became y.
Yeah, the power was a and became y, and the product was over y, but it became a. Right? So yij can be 0 or 1, and aij can be 0 or 1. So you can just rewrite terms like this. Right? So the first term here is p raised to aij for all ij such that yij is 1. So this is the same as aij being 1 and p raised to yij. So it's the same thing. Okay. And so now maximum log likelihood becomes this very nice quantity which is just a linear function of y, and the linear function depends on the observed adjacency matrix. Right? So it's a maximizing over y of some constant times all the yij's where aij is 1, and another constant where aij is 0, subject to the fact that y is a cluster matrix. So this is maximum likelihood. Okay. This is not computationally tractable to solve because there is no computationally easy way to search over all cluster matrices. Right. So we need to replace this y as a cluster matrix constraint. Okay. So where do spectral algorithms fit in this framework? Right. What is the relationship between this and spectral algorithms? So what spectral algorithms do as the first step is to take an SVD, and what the SVD is you are trying to minimize over all rank R matrices of aij minus yij the whole square, and summed over all the edges, right? So this is a non-convex problem because the rank R matrices are a non-convex set, right? But the so-called miracle of SVD is that this is still tractable to solve, and in fact you can solve it pretty fast for a sparse matrix, right? But unfortunately the miracle of SVD is just that, it's just a miracle in the sense that it's a one-off thing, right? Any variation of this theme and we do not have a tractable algorithm, right? So if instead of just the sum of square errors I wanted a weighted sum, or I wanted a sum of say absolute value or anything of that sort, is NP hard, right? And so what our algorithm is trying to do is trying to find a rank R matrix that solves a weighted sum of errors, right? And so this is not so there is no SVD like method which can do this, right? So instead what we need to do is we need to pose it as a convex optimization problem, right? Because this is a linear objective and this is an irritating combinatorial term, and so we just replace it by convex relaxation, and the convex relaxation is the trace norm or the so-called nuclear norm. Right. It's just a sum of singular values of a matrix. So this is a convex program. The nuclear norm or trace norm is intuitively something that penalizes higher rank matrices. So if you have two matrices of the same Frobenius norm, but one has a lower rank, then it will have a lower trace norm. Okay. So yeah, and you know, so this is our algorithm. It's a convex program. We find a y, and it's a convex program over the space of matrices, and we will say it succeeds if the unique optimum of this convex program is a cluster matrix and is the true one, right? And otherwise we'll say it will fail. Okay.
Tell us about lambda C1 and C2 then.
So C1 and C2 I've already told you about. C1 and C2 are just these quantities for P and Q.
We don't know how to pick P. We don't know P and Q.
Yes. So yeah. So for this theorem, okay. You can either think that P and Q is given to you, or you can estimate it from, the given graph.
Is Y also symmetric, and do you impose that?
Yeah. So actual cluster matrices have several more properties. They are symmetric. They are positive definite, because they are block of ones, and each block is a positive definite block. So the overall matrix is also positive definite. Yeah. So there are all these extra properties. We don't impose it because it makes the convex program harder to solve. But that's not the real reason. The real reason is that even if you do impose it, we don't get better performance results. In fact, the same convex program with these extra conditions has been analyzed by another group, and they could not get the same guarantees. So it seems hard to use those analytically. And the positive definite constraint will definitely make the convex program harder to solve. Okay, so hopefully the algorithm is clear, and our performance analysis is to see under what conditions on the three parameters of interest P, Q, and K does this program actually work, right? And which means that when does it recover the exact cluster matrix exactly as the unique optimum? Yes.
Is there a rate at which the regularization thing should change?
Yeah. So lambda is just 48 times square root n for our results. So yeah, I mean it's not a magic parameter. It's 48 times square root n. Okay. And we can get that just from the fact that the two quantities should balance each other on average. So okay. So here's our theorem, and it says that our program succeeds the moment the difference P minus Q is bigger than some universal constant alpha that depends on nothing else times P 1 minus Q n divided by K and log square n. And we also have a way to estimate P and Q from the graph itself. So if you are given a graph and you don't know P, Q, and K, but you know that it comes from some stochastic block model, then you can look at the empirical eigenvalues and you can get a P hat and a Q hat. And they will be, and if the original graph satisfies this, then the P hat and Q hat will also satisfy it, and we will be able to. So you can get an overall theorem. Okay. So I'm not going to spend too much time on explaining the theorem because I've in a sense already explained it to you. This is what one can imagine to be the limit of a spectral algorithm, maybe modulo log factors. Okay. Maybe in the interest of time and because I want to specify an open problem, I will skip this slide on remarks. Okay, so a little bit about the proof technique. How do we prove something like this? Like how do we prove something is the optimum of a convex program, right, with high probability? So if I have a convex function and I want to say that a point x is the minimum or the optimum, right, then the first order necessarily insufficient conditions is that 0 should lie, that the derivative of that point should be 0, right, or 0 should be the gradient of that point. We are dealing with non-smooth functions which are continuous but which may not have a derivative, but that's fine. They have a subgradient, and so all you need is that 0 lies in the subgradient of that point. Okay. So now what we can do, so the proof goes as follows. Look at this convex program. Now we already know what we want the optimum to be, right? We want the true cluster matrix to be the optimum. Okay, so we can write down a subgradient of this at the true point and then see if that's 0 or not. Right? So that should be pretty simple to do. It's not as simple as it would have been if it was smooth. Because it's not smooth, what that boils down to is this. So the first order necessary and sufficient conditions are that y star, which is the true matrix, is the unique optimum if and only if there exists some matrix W which satisfies a bunch of properties. I have 5 minutes left. Okay, which satisfies a bunch of properties, and essentially those properties are that within the true clusters, its value should be less than something that depends on A. Outside the true clusters, it should have a value which is something else, but it should be bigger than something else that depends on A. And its maximum eigenvalue should be 1, and it should be perpendicular to the original cluster matrix. By what I mean by perpendicular is that the rows and columns of W should be perpendicular to the rows and columns of Y star. Okay, so if you can find such a magic matrix W, then Y star is the unique optimum, and vice versa. Okay, so okay, that doesn't. So what do you do with that? Right. So now the problem becomes finding such a matrix W. If I can construct a matrix W and show that it satisfies these properties, then I'm done. So that's approximately the outline of the proof. It doesn't fully work because it's pretty hard to find a W which satisfies these conditions. So what we need to do is we need to change the conditions a little bit, right, by relaxing this orthogonality constraint but tightening the inequality constraints. So you can do it in a way that still makes it now only a sufficient condition, not a necessary condition, and then find a W, and then essentially make a W by adding 3 matrices, each of which is the sum of ideal elements. And this is a bit complicated, but it's a bit complicated to explain, but it's pretty easy to work out. And then use matrix concentration results or results on the concentrations of eigenvalues to actually show that the maximum eigenvalue is less than 1. Okay, the empirical performance in the interest of our method beats the best spectral algorithm so far, and I mean obviously it beats S-link as well. In the interest of time, I'll not go over this, but I'll mention something about extensions. So one extension is it kind of looks stupid, which is that if I have a problem that I can already solve, and if I make the problem easier, I can still solve it. So what I mean by that is that, say we have parameters so that my algorithm works. Now if a deterministic adversary goes in, but he is a deterministic adversary in a good way, which is that he increases the density within clusters and decreases the density outside clusters, then the algorithm will still work. Okay, what's the point of that? Well, the point of that is that every other spectral algorithm cannot be guaranteed to work with this adversary, right? Because when you have an adversary of this type, he can really mess up the eigenvalues in a way that cannot be predicted. We also have extensions to the case where there are outlier nodes that don't belong to any cluster. So this makes this algorithm useful even for finding dense subgraphs, even though you may not have a clustering of the whole matrix. Okay, do I have 2 more minutes? Okay, so I just spent 2 minutes on what I think is an interesting open question. It's not an open problem because it's a little bit, it's a bigger area, I think. Okay, so here is an algorithm that's empirically better while still being maximum likelihood, right? So another way of writing maximum likelihood using the low rank constraint is this way, right? So we saw that the likelihood term is C times A minus a low rank matrix, right? And so what you could do is you could impose the low rank constraint explicitly by saying that the variable that you're trying to find is not a matrix Y whose rank is low, but is a matrix U transpose, right, where U is a tall matrix. So I can explicitly write a low rank symmetric matrix as U times U transpose, take U to be my variable, right, and write the maximum likelihood in terms of U, and that's what it looks like, right. So this is, and this C times A is the element wise product, so SVD will still not work, right. Okay, but now I can write in terms of U. This is not a convex program because U transpose is not a convex object, but what you can still do is kind of this kind of an iteration, which you can think of as alternating minimization, right. Like find some initial u, and then keep updating in this way. And this is really nice because it has a an almost fully distributed implementation, where the u of each so each node has an r length vector that it keeps updating based on the r length vector of its neighbors, and one global number. Okay, so at every iteration you have to calculate one global number, give it to all the nodes, and then each node updates based on its neighbors. So this is super scalable. We have implemented this on graphs with millions of nodes, and it actually works better than the convex program.
Is that supposed to say ut plus 1 is argmin?
Yeah, sorry, argmin. Yeah, not min. Argmin. And so my kind of open question is, we now have a kind of semi-local algorithm on a graph, and the graph is locally tree-like. And so, can a locally tree-like line of analysis tell us something about such a procedure? Right? And the only kink in this thing is that there is this one global parameter that keeps changing. So we need to, if you can incorporate that, I believe this is pretty close to state of the art in terms of what you can do with large graphs. Okay, so I'll mention another open problem, which is lower bounds for this kind of problem are not known. Okay, thanks.
Questions?
You assume that in the cluster the probabilities P is the same. If it's different, does that change anything, or?
Right. So this is where that thing happens. So if they're all different, then the P in my theorem can be replaced by P min, which is the minimum across the clusters, and Q can be replaced by Q max, because I could always generate your graph by first taking my graph and having a good adversary. Yeah.
Many real-world networks have a lot of spread in degrees. Would you be able to incorporate that?
Right, that's a good question. There has been analysis of spectral clustering with SVDs, but with different degrees. So you could always run my algorithm, that's fine, right? But for my theorem, I'm not sure. I guess it depends on the degree distribution, but I have not looked at it.
The structure of the clusters.
Yeah, it depends on how the degree distribution interacts with the cluster size in a way that's not immediately obvious.
Any questions? Thank you very much.